Hello. Today we're going to talk about 14.2 limits and continuity. And when we're working with limits of multivariable functions, we have one really important thing to remember right away or to know. L'Hopital's rule is not used if we're working with multivariate functions. The only time we can use L'Hopital's rule is if we're dealing with a single variable function like we did in Calc 1. So, we will have some techniques that we'll use that may get us down to a function that has just one variable, and then we can use L'Hopital's rule, but not before then. So the limit of a multivariate function is a bit more complicated because what happens is our domain is higher than dimension 1. So in single variable calculus, we looked at, so in single variable, we looked at things like the limit as x approaches 0 of some f of x. And so if you look at a picture of what that means, if the value x equals 0 is right at the origin, or really anywhere along the y-axis, but really we're just concerned with x approaching 0, so we're on the x-axis, then we can approach 0 from just two directions, from the left and the right. That's it. There's no other way to approach 0 if you're just looking at x approaching 0. But when we get to multivariable and we're looking at an ordered pair x, y, trying to approach some point AB, then, for example, I've got this picture right here where the point AB is right here in the first quadrant, and there are four different paths shown, and those are supposedly paths of like x and y approaching this point AB. But those are just four. They're actually like an infinite number of ways for us to approach this point. So many ways, okay? An infinite number. And so that makes things harder to determine. Like when we're just looking at x approaching 0, it either does, like either the function value or the limit is going to exist as x approaches 0, or it doesn't. But in our case, we don't get a definitive answer very easily every time. So we have some strategies. Now, to show that a limit does not exist, what we're going to do, so we want to show that a limit does not exist, we have to find two different paths on which f of xy has different limits. That's the idea. Okay, so we would have xy approaching some number. We could even draw this idea over here. And we could put AB. Well, I'm just going to even put it like down here. So as we could have xy approaching along the x-axis. We could have xy approaching along the y-axis. We could have xy approaching along the function y equals x, or along the function y equals x squared, or even x equals y squared, like so many different ways for us to approach this point. Now, what we're not seeing here is the z value that we would get, right? Because we're in 3D, technically. F of xy is a three-dimensional function. Our domain is just 2D, and that's why we're looking at these 2D images. So what's happening is we're approaching, xy is approaching 0, 0 from all these different directions, and we may be getting different levels of z showing up there. I guess maybe a better way to see that is if we had, say, an octant, right? This is also kind of hard to draw, but let's say that, again, we're aiming towards the origin, and we could approach from along the x-axis, or from along the y-axis, or from along the line y equals x, or y equals x squared, and so on and so forth. But then what if we decide to like approach from x equals y squared, and we end up here? Like our limiting value has a higher z value. Maybe we get like 2 instead of 0. So that's kind of the idea here, that we could be approaching, and we're approaching along the xy plane, and then all of a sudden we get this value that is way up here. Okay, that would be a different number. So if we do end up getting 2 different limits, and so that what that means is that the value of our limit is dependent on the path that we travel on. And in that case, if a limit is path dependent, that means the limit does not exist. So limit has to be the same regardless of the direction that you're approaching from. It should always be the same. If it is, then we know that the limit does exist. So to choose these paths, I've already mentioned a few. Usually we'll look at like x equals 0. X equals 0 is approaching along the y-axis. Y equals 0 is approaching along the x-axis. We could approach along the line y equals x squared, x equals y squared, etc. This can go on and on and on. But the point of these particular paths is that we're having x, y approach 0, 0, and all of these paths go through 0, 0. So I wouldn't pick a path that doesn't go through the point that I'm trying to get to, right? I have to pick a function that actually goes through that point, and then I can actually take a limit then. Okay, we'll do some examples with the paths, but for now, let's keep looking at our strategy. So let's say that we want to show that a limit does exist. Sometimes this is easy, and other times this is really hard. If we're lucky, then we'll just have to do some algebra. And then we'll be able to just evaluate directly to find our limit. We won't be worried about paths. We'll get what we need right away. Another thing that could happen is if the point AB is the origin, 0, 0, then another strategy we could use. So let's see really quick. Algebra to evaluate directly. In this next one, another strategy is to rewrite the limit in polar coordinates, where x is now r cosine theta and y is r sine theta. And the reason why this works is because then no matter how xy is approaching 0, 0, r, the radius, goes to 0. So then we can look at a limit as r goes to 0, and this becomes a single variable function. Yes, there are thetas in there, but we're looking at a limit as r goes to 0, and we don't really care about theta, so we don't consider it the variable of the limit. If that limit exists, then the original limit also exists, and they are the same values. So those are two of the lucky things that could happen. But if you're not lucky, then you're going to be choosing to try a lot of paths, at least 4 to 5 paths. And if you're getting the same limit every single time, and you've done like 4 or 5 paths, then you might be starting to think that your limit does exist. And if this is the case, you have to prove it. You have to use the squeeze theorem in order to prove that a limit exists. You can't just say, I tried 4 paths and I got the same number, so that's my limit. It doesn't work that way, because you only tried 4 paths, and there are an infinite number of paths, infinite number of ways to approach one point on an xy plane. So trying 4 isn't really a whole lot of work when you compare that to infinity. And nobody's going to sit down and approach on an infinite number of paths, so we have to have a way to prove things, and we'll use the squeeze theorem. So we're going to go through a bunch of examples where we see all these different cases, like direct evaluation works, or algebra works, or the paths work, or polar coordinates work, or we end up using the squeeze theorem. All the same limit laws that we saw in Calculus 1 apply here. So These are your sum laws, difference laws, constant multiple law, the product law, and the quotient law. Make sure you are comfortable with all of those. And then the other thing is, and this is my law right here, and it is called the notation law. You are in Calculus 3 now. There is no excuse for using improper notation when evaluating limits. I know that in Calculus 1, it was very tempting to drop the limit before you've evaluated, or you already evaluated and you're still writing the limit. So we've got to practice proper notation. Okay. In these examples, we're going to find the limit if it exists, or we're going to show that the limit does not exist. In every single case, we should always try direct evaluation first. If that doesn't work, then we see if algebra is our friend. If that doesn't work, then we start using the paths. And that's your order, okay? So let's see. The limit as xy approaches pi and 1/2 of e to the xy sine of xy. Well, we're going to try direct evaluation first. So if I do direct evaluation, I get e to the pi times 1/2, that'll be pi over 2, times sine of pi over 2. Well, sine of pi over 2 is 1, so I just get e to the pi over 2. That's my limiting value. I'm done. That was a nice, easy problem. So we had direct evaluation for this problem. The second problem, let's see if we can just plug things in. So if I plug in x equals 1 and y equals 2, I get 2 minus 2 on top, and I get 4 minus 4 on the bottom, which is 0 over 0, and that is indeterminate. So this is indeterminate. But you cannot use L'Hopital's rule. Okay? Not allowed to. However, we can use algebra. We can look at our function carefully and see if there are any things that we can do. And by things, I mean factoring or rationalizing a denominator or a numerator or something. Try something, okay? I'm looking at this denominator and I see a difference of squares. So I'm going to try that. So we rewrite the limit because we're not evaluating the limit. We're working with the function. So we're still looking at the limit as xy approaches 1, 2. The numerator is staying the same, 2x minus y. The denominator is a difference of squares, so it will factor as 2x minus y times 2x plus y. The 2x minus y's are going to divide out, and now I'm looking at the limit as xy approaches 1, 2 of 1 over 2x plus y. And now that we've done something, like anytime you do something, like in our case, we factored. First, clean up the mess that you just made. See if anything simplifies. And second, try direct evaluation again. If it is rationalizing, you're going to clean up your mess first, and then you're going to try direct evaluation. So anything you try, clean up, then evaluate. If it doesn't work, then we'll see what we have to do. So in this case, I've cleaned up. I'm going to go ahead and try a direct evaluation again, and I get 1 over 2 plus 2 for a final answer of 1/4. That's my limiting value. I'm done. So algebra led to direct evaluation. All right, next problem. The limit as xy approaches 0, 0 of 2xy over x squared plus 3y squared. Now, if I do direct evaluation here, I get 0 over 0. And again, I can't use L'Hopital's rule, so this is just indeterminate, and I have to find a new technique. So I start looking closely at my function, and I'm asking myself, does this factor at all? Does anything simplify? Nothing simplifies, okay? So no direct evaluation or algebra will help us here. So I have to try paths. Now I'm just going to keep a little picture over here of the different paths that I try, because I think it's important that when you do something abstract like evaluating a limit, you have an idea of what you're actually doing, okay? So we're going to try approaching, what is it, 0, 0? We'll try approaching along the x-axis first, okay? So the x-axis is where y is equal to 0. So we're fixing y to be 0, and then we're going to let x vary and travel to 0. So what that looks like is we have the limit of x0 approaching 0, 0. Everywhere there's a y, I'm going to replace it with 0. So when I plug in 0 to my function, I get 0 over x squared. Well, I should just simplify that first, because 0 over anything is just 0. And the limit of 0 is 0. So there's really no work to do there. The next path I'm going to try is along the y-axis. So I want to approach the origin along the y-axis, and on the y-axis, x is equal to 0. So again, I do the same thing, take the limit, and now x is being fixed to be 0 and y is varying. So it's the limit as 0y approaches 0, 0. Now I'm going to go through my function, and everywhere there's an x, I'm going to put in a 0. That gives me 0 over 3y squared. And 0 over anything is 0, and the limit of 0 is 0. Okay, two paths. I got 0 both times. I'm starting to think maybe it's 0, but it's not okay for me to make that conclusion yet. I need to try a different path. So I'm going to try y equals x. I'm going to approach along this y equals x path. So this is y equals x. And what that's saying is that I'm going to take the limit, and everywhere there is a y, I will replace it with an x. So it's the limit is xx approaches 0, 0, which is kind of weird. But it's all it is just replacing any y's with x's. So in my function, when I replace all the y's with x's, I get 2x times x in the numerator. In the denominator, we have x squared plus 3x squared. That is going to simplify a bit. I get the limit as xx approaches 0, 0 of 2x squared over 4x squared. Now, that fraction totally simplifies, and you should simplify it. Anytime there's like things that will cancel out, go ahead and do it. So when I do that, I get the limit as xx approaches 0, 0 of 1/2. And the limit of a constant is a constant, so our value is 1/2. So we tried a different path and we got a different limiting value. The limiting value is different on different paths. Therefore, oops, I forgot to put in the word paths. Therefore, the limit does not exist. And then I'm done with the problem. So that was one of those, like, I feel lucky because I only had to do 3 paths, and I was able to show that I got different limiting values, which means I'm done, because different limiting values means the limit doesn't exist. Okay, let's look at another one. In 4, we want to show that the limit does not exist. So again, we are going to go ahead and check to see if we can do direct evaluation, check to see if algebra will help us. We're going to check all the things. So with direct evaluation, I get 0 minus 0 on top, which is 0, and 0 plus 0 on the bottom, which is 0. So direct evaluation didn't help. I'm noticing that the numerator is a difference of squares, but it doesn't simplify with anything in the denominator, so algebra doesn't help. So direct evaluation and algebra do not help. So we have to try paths. And I always just start with the same ones. It's not very creative, but it teaches me how to be consistent and do the same thing each time rather than wondering, wait, what am I supposed to do? So again, I'm going to draw a little picture so we can see what's going on here. We're approaching 0, 0. I'm going to try along the x-axis first. So the x-axis is where y is 0. And that means I'm looking at the limit as x, 0 approaches 0, 0. So everywhere there's a y in my function, I need to replace it with 0. When I do that, I get x squared minus 0 squared over x squared plus 0 squared. That is a fraction that simplifies. So I get the limit as x0 approaches 0, 0 of 1. And the limit of a constant is the constant, so my value is 1. All right, now I'm going to try along the y-axis and see what happens. So on the y-axis, x is equal to 0. I look at replacing all x's with 0. So I have the limit as 0y approaches 0, 0. And I replace all my x's in my function as well. I get 0 squared minus y squared over 0 squared plus y squared. And that is a fraction which will simplify, so I do so. I get the limit as 0y approaches 0, 0. And this reduces to the number -1. And the limit of a constant is the constant, so my limiting value is -1. And what I can conclude here is that my limit value is path dependent. Sorry about that. Technical difficulties. Had to do a restart to get my pen working. I was just working through this problem here and got to the conclusion that I took two paths. I got two different limiting values, so that means the limit value is path dependent. And I couldn't write the word dependent because my pen wasn't working. So if the limit value is path dependent, this means the limit does not exist. And that's it. All we had to do was show that we got two different limiting values and we're done. Okay, let's look at this next one. In this next one, we have, let's see, direct evaluation will give us 0 over square root of 0, which is still 0 over 0. And so direct evaluation fails. There is no such thing as factoring anything in here. There's no algebra that can save us right now. So direct evaluation and algebra fail us for now. So we're going to try paths, and I'm going to introduce some new notation for you to try that is not violating limit notation, but it's a different way to write when you're dealing with limits. And it allows you to write a little bit less without writing something that is meaningless. You want your whatever you write to be meaningful mathematically. So here's what I mean. Number one, we are going to draw our little graph showing the paths. We are trying to approach 0, 0, and I am going to first approach along the x-axis. So x-axis, y equals 0. So I'm going to look at f of x, 0. So I'm just taking my function that I'm trying to find the limit on, and I am replacing all y's with a 0. When I do that, I get x times 0 over the square root of x squared plus 0 squared. So this simplifies to be 0 over x, and 0 over anything is 0. So what that means is that f of x comma 0 approaches 0, because the limit of 0 would be 0, as x goes to 0. So that's how I can write limit notation without having to write limit notation. This is like the one other acceptable way to write things. All right, now let's move to the y-axis and see if we get the same thing. So on the y-axis, we have x is equal to 0. So we're going to look at f of 0 comma y, which means that we're supposed to replace all x's with 0. So we get 0 times y over the square root of 0 squared plus y squared. That simplifies to be 0 over y, which is 0. That means that if I take the limit, if I'm going to take the limit as y goes to 0, my function f of 0y approaches 0 as y approaches 0. Okay, another path, I will go along y equals x. I'm going to run out of colors here. So along y equals x, I'm looking at f of xx. Okay, so everywhere I see a y in my function, I need to plug in an x. So this is going to give me x times x in my numerator, and then the square root of x squared plus x squared. Oops. I'm saying x squared, but my hand still wants to write y squared. Okay, and then I can simplify this. This is x squared over the square root of 2x squared, and that goes to x squared over x square roots of 2, and finally this simplifies to be x over the square root of 2. All right, f of xx, which is equal to x over the square root of 2, that's going to go to 0 as x goes to 0. So again, I'm still using my nice notation to be able to write this down a little bit faster. And I have a function now. I don't just have a constant, I have a function. And we know that if we take the limit of a function and we can do direct evaluation, then we do so. So that's all I did. It's just direct evaluation. Let x go to 0. So I'm getting the same limiting value, but this is just 3 paths. I need to try 2 more. I'm not allowed to stop yet. Okay, I am going to try y equals x squared.